Hey, this video contains solutions for some problems from Chapter 11. And let's start with number 43, working with conservation of angular momentum. So in this problem we have two skaters who are going to grab onto a pole, one of them here, one of them here. This one has a velocity of, what's their velocity? 1.4 meters per second. And this one has the same velocity but in the opposite direction of 1.4 meters per second. They both have a mass of 50 kilograms. And the length of the pole is 3 meters. So the radius of the circle that they're going to move in is, this is the question, part A. The radius is 1.5 meters. And that's not completely obvious, I think, if you just think, well, it's just half the length of the pole. Well, it's half the length of the pole only because they have the same mass. If they had different masses, then it would be the they would move around the center of mass, so it would be a little bit more complicated there. They would not be moving in the same circle in that case, but they have the same mass here, so the radius of the circle is just 1.5 meters. B, what's the angular speed of the skaters? Well, the angular momentum of the skaters is the angular momentum of skater 1. Now skater 1 around this rotational axis here, now that we've figured out where the center of the circle is around in this direction. Right? So we'll call that the positive direction. That is the sort of the default positive direction, right? Counter or anti-clockwise. So that would be the RMV of skater 1 plus the angular momentum of skater 2. And skater 2 is also going to be going in the same direction around the circle. So although they're going opposite velocities, their velocities have opposite directions. They're going the same direction around the circle. So that's R2, M2, V2. And it so happens in this situation that all the RMs and Vs are the same. So that's going to be 2 times the radius of the circle times the velocity of the skaters times the mass of the skaters. And that is 2 times 1.5 times 1.4 times 50. Oops, sorry, what am I doing in that screen? Let's try that again here. 2 times 1.5 times 1.4 times 50. So that's 210 kilogram meters squared per second. That's the total angular velocity, angular momentum, sorry, of the skaters. They wanted to know what's the angular speed of the skaters. The angular speed of the skaters would be the total angular momentum is conserved, so the initial angular momentum is equal to the final angular momentum, which we could calculate like so, because it's two particles rotating on a fixed axis. So that 210 is equal to the I omega of the skaters. And the I, we have two particles, right? If we wanted to calculate the rotational inertia, it's just mr squared plus mr squared. and they both have the same mr squared, so that's 2m r squared times omega. So that's 210 divided by 2 times 50 times 1.5 squared. And that's 0.93 radians per second. Part C. What's the kinetic energy of the two-skater system? Well, the rotational kinetic energy of the two-skater system is equal to 1/2 I omega squared. That's equal to 1/2 I omega squared. So there's my omega, so if I square that and then multiply by 1/2 times 2 is 1, sorry, and that's times 50 times 1.5 squared. And that's 98 joules. So I have to hit enter a couple extra times here because of the smudge on my screen there. So 98 joules. Part D. What's their angular speed? Now they're going to scoot in on the pole until they're only 1 meter apart. So now the distance between them is only 1 meter. But we know that angular momentum is conserved here, so that means the angular momentum before, which is the angular momentum before, is equal to the angular momentum after. And I know the angular momentum before, I found that, that's 210. It's going to be equal to the angular momentum after. And that's their new moment of inertia, which is different now. That's going to be here 2, because they're going to have the same moment of inertia. 2 particles that have now an m. r, their radius is now only 1/2 meter. So that's the mr squared for each skater times 2, because there's 2 of them, times the new angular velocity. So that looks like 210 divided by 2 times 50 is 100 times 0.5 squared. So the new angular velocity is 8.4 radians per second. I think is that what they were asking for? Yes, in part D. And notice here, compared to their original angular velocity, that's a big increase. So why did that happen? They significantly decreased their moment of inertia, so that's going to increase their angular velocity. Part E is asking what's the kinetic energy of the system now. Well, now the kinetic energy would be equal to 1/2 I omega squared, which is now 1/2. The new I is 2 times 50 times 0.5 squared times their new angular velocity squared. So that is 1/2 times 2 times 50 is 100 times 0.5 squared is 0.25 times 8.4 squared. That's 882 joules. So that's a big increase in energy. They went from 98 joules of rotational kinetic energy to 882 joules. And then the last part is, where the heck did all that extra energy come from? Well, it's not easy for these skaters to scoot toward the inside. It's difficult for them to do that, to pull in toward the middle as they're rotating. So where did that come from? It came from the energy of the skaters. You could say that the skaters did positive work on the system. If the skaters were completely lacking in any energy that they were capable of adding to the system, then it would not be possible, right? They would have to have some energy to expend to pull themselves toward the inside and thereby increase the kinetic energy. So that's where the energy came from. Right. Number 45. Number 45, a man stands on a platform that is rotating without friction with an angular speed of 1.2 revolutions per second, and his arms are outstretched and he holds a brick in each hand. The rotational inertia of the system of the man, bricks, and platform about the central vertical axis is 6 kilogram meters squared. If by moving the bricks the man decreases the rotational inertia of the system to 2, so that's the rotational inertia before he moves, and then afterwards he decreases it to 2 kilogram meters squared. What are the resulting angular speed of the platform and the ratio of the new kinetic energy of the system to the original kinetic energy, and what source provided the added kinetic energy? So I think we know the answer to part C already, right? The man had to pull those bricks in, right, which is not easy to do when you're rotating. So, part A, the new, we have I omega before has to equal I omega after. So that gives us 6 times 1.2 is equal to 2 times final omega, so that's what, 3 times 1.2, so that'd be 3.6 revolutions per second. And you could change that to radians. Sorry, I don't know, I have an equal sign there. 3.6 revolutions per second. You could turn that into radians per second. That'd be fine if you did that. B, the ratio of the new kinetic energy of the system to the old kinetic energy. So that's kinetic energy final over kinetic energy initial. So that's 1/2 that would look like this. The 1/2s cancel if we're just finding the ratio. So the final rotational inertia was 2. The final angular velocity was 3.6. And the units will cancel here, whatever they are. So I can use the revolutions per second over 6 times the original was 1.2. And I think here, if you look at the ratio like this, you can kind of see what's happening here. This is 1/3, and this is 3/1, but these are getting squared. So that's going to be 3. 3:1 or 3 is that ratio. See? What source provided the added energy? It was the internal energy of the man, right? The man did positive work on the system. Right? He couldn't move those bricks in toward the center for free, right? That required energy to do that. So that did positive work on the system. Let's see, what's next? Number 49. See if we can squeeze it in down here. Two discs are mounted like a merry-go-round on a low friction bearings on the same axle and can be brought together so that they couple and rotate as one unit. First disc with rotational inertia. So the rotational inertia of the first disc is 3.3 kilogram meters squared about its central axis, is set spinning counterclockwise at 450 revolutions per minute. So we may have to change those units, we'll see. Second disc with a rotational inertia of 6.6. So bigger disc, apparently, more massive, bigger radius, something. About its central axis is set spinning counterclockwise. So let's see, are they both going counterclockwise? The first one is set spinning counterclockwise. The second one is also counterclockwise, so the same direction. So I'll keep the same sign on those. We'll take counterclockwise to be the positive direction. Revolutions per minute. They then couple together. So what's the angular speed after coupling? Well, we know that the total angular momentum before is equal to the total angular momentum after. The total angular momentum before is I1 omega 1 plus I2 omega 2. Sorry, that should be, geez, that's the second disc, right? And then they're going to couple together. Now, rotational inertias add together, right, just like masses do. So afterwards, they stick together. So I'm just going to have I1 plus I2. That's the total rotational inertia. And then that's our omega final. Right, so I can calculate that. So, sorry, there's a hair attached to my calculator. There we go. Let's see, so 3.3 times 450 revolutions. These are the same units, so I think I'm going to be okay here if I use those units. Plus 6.6 times 900. That's the total rotational inertia in these units, right? I times omega, so it's not exactly SI units, but all our units are the same, so we should be okay if we then divide by the total rotational inertia, which is 9.9, and that will give me the final, the angular velocity afterwards, and since I used these units, that will be in revolutions per minute. That's part A. If instead the second disc is set spinning clockwise at 900, then what then is the angular speed and direction of rotation after they couple together? Well, I'll take clockwise to be the negative direction, so the calculation will look exactly the same as this, except my I omega, this will be 3.3 times 450 plus 6.6. And now since this one is going in the opposite direction, we'll have to call that negative. I'll call clockwise the negative direction, right? And that's equal to the sum of their moments of inertia times the final. And we'll run that calculation. So now I have 3.3 times 450 plus 6.6 times negative 900, and then divide that by 9.9. So now that gives me negative 450 revolutions per minute. And that negative sign means that it's going clockwise, because we took positive to be the counterclockwise direction. And that's it for that one. And just check the answers real quick for that and make sure we're good. Yep. Looks good. Next we have, 53 and 61. 53. A uniform thin rod of length 0.5 meters and a mass of 4 kilograms can rotate in a horizontal plane about a vertical axis through its center. So it can rotate around that axis right there, right through the center. The rod is at rest when a 3-gram bullet traveling in the rotational plane, so traveling in the plane of the rod, is fired into one end of the rod. So it's going to embed itself into one end of the rod. As viewed from above, the bullet's path makes an angle of 60 degrees. So that's the V of the bullet. And this angle here is 60 degrees. If the bullet lodges into the rod and the angular velocity of the rod is 10 radians per second immediately after the collision, what's the bullet's speed just before impact? Okay, so before the collision, we have the angular momentum of the bullet with respect to this axis. And afterwards, we have the angular momentum, capital L. So this is small l because it's a particle traveling with respect to that axis. And then afterwards, we have capital L. It's an object rotating in that plane. I'll just call that L final. Okay, so how do we calculate the small l for the bullet? Well, that's r mv sine theta. And then the L final will be the I, but that's the I of the rod plus the bullet, or the bullet lodged into it. Although the bullet is so small, it's not going to make much of a difference, but we should include it there just to be complete about it. And then times the final angular velocity, and they gave us that. All right, so let's see what we can do with this. So the R for the bullet, when the bullet hits the block, the R vector for the bullet is this vector right here, which has a magnitude of half the length of the rod, which is 0.25. The mass of the bullet, which I think I didn't write down here, is 0.003 kilograms. The velocity of the bullet, that's what we're looking to find. And the sine of theta, so that angle here, that's the angle between the r vector, it's r cross p, but p and v, the momentum vector and the velocity vector, always have the same direction, because momentum is just mass times velocity, and mass is not a vector. So you could just say, oh, well, the angle between them is 60, and that actually works out to be correct, but we really want to imagine the two vectors coming from the same point, and then by various geometry theorems, these would be alternate internal angles, so this is also 60 degrees. You can see clearly that that's also 60 degrees. So that's the sine of 60. Okay, on this side of the equation we have, what's the rotational inertia of the rod plus the bullet? Well, the rotational inertia of the rod, thin rod about its center, and that's one of the ones we're supposed to know, that's 1/12 m L squared. That's the rotational inertia of the rod. And then we add the bullet as a particle, which has, so we add mr squared for the bullet. It's mr, that's at a radius of 0.25 squared times the final angular velocity, which is 10. So we've got everything in here except for the v. So v is equal to this whole expression divided by 0.25 times 0.003 times sine of 60. So let's see if we can do that. So 1/12 times 4 times 0.5 squared plus 0.003 times 0.25 squared. And again, if you left this out completely because this is so light, the bullet is so light compared to the rod, it probably wouldn't affect the answer to any decimal places that we care about. But we'll include it because it should be there. So that's the whole I of the rod plus block, rod plus bullet times 10 divided by 0.25 times 0.003 times the sine of 60. And I'm just going to really quickly check, yep, I'm in degree mode. And then let's see, that's the velocity of the bullet was 1,200 and let's call that 90, I guess, if we're going to round to 3 sig figs meters per second. And the book called that 1,300. So same difference. That is a good problem. That's a classic conservation of angular momentum kind of situation there. And then our last one is at number 61. Yes. In number 61, we have a rod and a little ball here. The rod is going to swing down and whack into this little ball sitting here. It's going to rotate down this way. On the uniform rod, which has a length of 0.6 meters, a mass of 1 kilogram, rotates in the plane of the figure about an axis through one end. Right, there's the axis there. So it's going to swing down and then crash into that rod. With a rotational inertia of 0.12 kilogram meters squared. I wonder why they had to tell us that. I wonder. The rotational inertia of a rod about one end is 1/3 ml squared. So 1/3 times m, which is just 1, times L squared. Yeah, I mean, I don't know why they told us that. It is 0.12, so we could have calculated that, but they told us anyway. As the rod swings through its lowest position, it collides with a wad of putty, which has a mass of 0.12 kilograms. No, 0.20, sorry, wrong number there. 0.20 kilograms. and it sticks to the end of the rod. They stick together, so this is an inelastic collision. If the rod's angular speed just before the collision is 2.4 radians per second, what's the angular speed of the rod-putty system immediately after the collision? All right, so before the collision, what kind of angular momentum do we have? Well, we have the angular momentum of the rod, which is an object rotating on a fixed axis. So that's a capital L kind of angular momentum. And then afterwards, we have a rod with this bit of putty stuck to it. That's also a capital L kind of angular momentum. So let's see if we can fill this out. So for the rod beforehand, we have an I omega before. After the collision, we have an I, that's the same I for the rod, plus the rod now has this wad of putty stuck to it. So that's an mr squared, adding this as a particle to the end of the rod. It's m r. That's the length. The r for the putty is the full length of the rod, right? That's the distance from the axis to the location of the putty. 0.6 squared. That's the new I times omega. Right? Just like a momentum, like an mv equals mv, right? I omega equals I omega. And they would like to know what this is. Is that the only part of this? Yeah, I'm surprised this has 2 dots. This seems like a pretty easy problem for a 2-dotter. But so that's 0.12 times 2.4 divided by this expression here, 0.12 plus 0.2 times 0.6 squared at 1.5. radians per second. And that's it. Conservation of angular momentum. That's how you do it. Sometimes you have small l equals big L, sometimes you have big L equals big L, you could have big L equals small l. These L's can be equal. We just calculate them a little bit differently. Units are the same.